Hello there, and welcome to the Scientist Sleepy. Tonight, we embark on a gentle exploration into one of the universe's most profound and mysterious phenomena, the enigmatic workings of black holes. We will drift through the fundamental principles that govern these cosmic titans, uncovering surprising truths about how they shape the very fabric of the universe around them. Prepare to be captivated by the quiet, cinematic wonder of the cosmos, as we delve into facts that are both awe-inspiring and deeply philosophical. Let us begin our drift. Black holes are not cosmic vacuum cleaners. The popular image of a black hole is often one of an insatiable cosmic drain, a celestial vacuum cleaner indiscriminately sucking up everything in its path. While this imagery is evocative, it's not quite how these enigmatic objects truly function. The reality, as is often the case in the universe, is far more nuanced and in its own way even more profound. Black holes exert gravity, a force that pulls objects towards them. However, this pull is only truly inescapable once you cross a certain boundary. Imagine the Earth's gravity. It keeps us grounded, but it doesn't actively pull you off the street if you're just walking by. You have to fall towards it or be launched towards it. Similarly, a black hole's gravitational influence extends outward, just like any other massive object. If you were far enough away from a black hole, you could orbit it safely, much like a planet orbits a star. The vacuum cleaner analogy breaks down because it implies an active, aggressive suction that extends indefinitely. In truth, the gravitational pull of a black hole follows the same fundamental laws as any other source of gravity. The difference lies in the extreme concentration of mass within a tiny volume, leading to incredibly strong gravitational fields, but these fields still diminish with distance. It's only when matter gets very close, approaching the event horizon, that the inescapable nature of its gravity becomes apparent. So, rather than an active, indiscriminate gobbler, think of a black hole as an extreme gravitational well. Objects don't get sucked in from vast distances. They must venture too close, or be on a trajectory that leads them into its overwhelming embrace. This distinction is vital for understanding the dynamic and often intricate interactions that occur around these cosmic behemoths, where matter can orbit, heat up, and even be ejected, rather than simply being devoured. The universe is not a place of passive consumption by black holes, but rather a stage for the profound interplay of gravity and matter, where proximity dictates destiny. In the quiet gravitational embrace, destiny is not a chase, but a chosen proximity. The event horizon is a point of no return. Imagine, if you will, a boundary not of solid matter but of pure consequence. This is the event horizon of a black hole. It is not a wall you can touch, nor a surface you can stand upon. Instead, it is an invisible sphere, a cosmic threshold, beyond which the grip of the black hole becomes absolute. To cross this boundary is to surrender all possibility of escape. The very fabric of spacetime is so dramatically warped here that all paths, all directions, lead inward, inexorably towards the singularity at the heart of the black hole. Light itself, the fastest thing in the universe, cannot outrun the gravitational pull at the event horizon. If you were to shine a flashlight outwards from within this region, the beam of light would simply curve back in, a prisoner of the black hole's immense gravity. This is why black holes appear black. No light can escape to reach our eyes. The radius of this sphere, the distance from the singularity to the event horizon, is known as the Schwarzschild radius, and it is directly proportional to the mass of the black hole. A more massive black hole has a larger event horizon. For a black hole with the mass of our Sun, the Schwarzschild radius would be about 3 kilometers. For the supermassive black hole at the center of our Milky Way, Sagittarius A, it's about 12 million kilometers. It's a conceptual divide, a one-way street into the abyss. There's no warning sign, no physical barrier, only the inescapable reality of space-time curvature. Once you've crossed it, the universe you knew, the stars, the galaxies, the very concept of out, recedes into an unreachable past. The journey into a black hole is, in essence, a journey into a region where time and space swap roles in a profound and disorienting way. From an outside observer's perspective, an object falling towards a black hole would appear to slow down as it approached the event horizon, its light red shifting until it effectively freezes at the boundary, never quite crossing. This is due to time dilation, a consequence of the extreme gravity. But for the object itself, time would continue to pass normally until it crosses the horizon, at which point its fate is sealed. The event horizon is a fundamental concept in understanding black holes, representing the ultimate dominion of gravity, a cosmic boundary where escape becomes not just improbable, but physically impossible. It's a reminder of the universe's most extreme phenomena, where the laws of physics as we experience them are pushed to their absolute limits and beyond. Here, the universe draws a line, and all journeys beyond it lead only to the profound unknown. Singularity, where our understanding of physics breaks down. Imagine, if you will, the very heart of a black hole, not the fiery, swirling disk of gas that often captures our imagination, but the absolute, unfathomable core. This is the singularity, a concept so profound, so alien, that it represents the ultimate frontier of our scientific comprehension. At this point, the laws of physics as we know them, the very bedrock of our understanding of the universe, simply cease to apply. Think about gravity. We understand it as a force that pulls objects together, a force that weakens with distance. But at the singularity, gravity becomes infinitely strong. All the mass of the collapsed star, or whatever cosmic material has contributed to the black hole's formation, is compressed into a point of zero volume and infinite density. This is a concept that strains our very ability to visualize. Our equations, which so beautifully describe the motions of planets and the behavior of light, falter and fail when confronted with the singularity. We speak of infinite density, but what does that truly mean? It's beyond our everyday experience, beyond our ability to measure or observe directly. It's a point where space and time, those fundamental dimensions we use to navigate our reality, are warped to an extreme that is beyond our current models. General relativity, Einstein's masterpiece that describes gravity as the curvature of spacetime, predicts the existence of singularities within black holes. However, even Einstein himself acknowledged that this was a sign that his theory was incomplete at these extreme conditions. It suggests that a more fundamental theory, perhaps one that unifies gravity with quantum mechanics, is needed to truly understand what happens at the singularity. We can describe it mathematically, we can predict its effects on the surrounding spacetime, but the physical reality of a point of infinite density and curvature remains a profound mystery. It's a place where the very fabric of existence is stretched to an unimaginable limit, a place where the known universe dissolves into the unknown. The singularity is not just a theoretical concept. It's a stark reminder of the vastness of what we don't know, a testament to the universe's capacity for the utterly incomprehensible. It's where the elegance of scientific law meets the ultimate enigma, a silent, invisible heart of pure cosmic paradox. Within the silent heart of the cosmos, a point exists where all known laws surrender, a testament to the universe's boundless and beautiful mystery. Spaghettification, the stretching and tearing of matter. Imagine, if you will, the profound and almost poetic violence that can occur when matter ventures too close to the insatiable maw of a black hole. This phenomenon, known by the rather evocative name of spaghettification, is a direct consequence of the extreme gravitational gradients that characterize these celestial enigmas. What this means, in essence, is that the gravitational pull exerted by a black hole is not uniform across an object. The part of an object that is closer to the black hole experiences a significantly stronger pull than the part that is farther away. This differential force, this tidal effect, is what leads to the dramatic stretching and tearing. Consider an astronaut, for instance, falling feet first towards a black hole. As their feet get closer to the event horizon, the black hole's gravity tugs on them with an immense force. Meanwhile, their head, still a little further away, experiences a weaker pull. This difference in gravitational force, this immense tidal stress, begins to stretch the astronaut's body along the direction of the fall. Simultaneously, forces perpendicular to the direction of the fall would compress the astronaut, squeezing them inwards. The net effect is a distortion akin to pulling a piece of taffy, or indeed, a strand of spaghetti, until it snaps. The intensity of this stretching depends crucially on the size of the black hole. For smaller, stellar mass black holes, the event horizon is relatively close to the singularity, and the gravitational gradient is incredibly steep. This means that spaghettification would occur even before an object crosses the event horizon, tearing it apart in a spectacular display of cosmic destruction. For supermassive black holes, however, the event horizon is much larger, and the gravitational gradient is gentler at the horizon itself. An astronaut falling into a supermassive black hole might actually cross the event horizon intact, only to be spaghettified much later, closer to the singularity. This difference is a fascinating illustration of how the scale of these cosmic objects dictates the nature of their gravitational influence. The process is not instantaneous, but rather a gradual, albeit rapid, disintegration. As matter approaches the black hole, it is first drawn into a swirling, incandescent disk known as an accretion disk. Within this disk, particles collide, heat up to incredible temperatures, and emit vast amounts of radiation. It is in this fiery maelstrom that the ultimate fate of matter is sealed. Individual atoms and molecules are subjected to these tidal forces, their bonds strained and eventually broken. The very fabric of the matter is stretched, elongated, and ultimately shredded into its constituent particles, which then spiral inexorably towards the singularity. This tearing apart is not just a physical process. It's a fundamental disruption of structure, a complete dismantling of organized matter under the most extreme conditions imaginable. The energy released by this process can be immense, powering some of the most luminous objects in the universe, such as quasars, which are essentially the feeding frenzies of supermassive black holes. The spaghettification of matter is, in many ways, the engine that drives the most energetic phenomena we observe in the cosmos, a testament to the raw power locked within the gravitational embrace of a black hole. It is a stark reminder that even the most robust structures in the universe are ultimately subject to the fundamental forces that govern space-time. In the stretching and tearing, even the most ordered forms dissolve into the universal flow. Time dilation near a black hole is extreme. Imagine, if you will, the gentle river of time. For most of us, it flows at a steady, predictable pace, a constant rhythm that guides our days and nights. But near a black hole, this river doesn't just flow. It twists, it churns, it warps into something utterly extraordinary. This phenomenon, known as time dilation, is one of the most profound and mind-bending consequences of Einstein's theory of general relativity. At its heart, general relativity tells us that gravity isn't just a force pulling objects together. It's a curvature, a bending of the very fabric of space-time caused by mass and energy. The more massive an object, the more it warps space-time around it. And black holes, with their immense density and gravity, create the most extreme curvature imaginable. To understand time dilation, let's consider a thought experiment. Picture two identical clocks, perfectly synchronized. One clock remains far away from any significant gravitational influence, perhaps floating in the vast, empty reaches of interstellar space. The other clock is brought closer and closer to the event horizon of a black hole. As the second clock ventures deeper into the black hole's gravitational well, time, as experienced by that clock and any observer near it, begins to slow down relative to the clock in deep space. It's as if the river of time itself is becoming sluggish, thick, and viscous in the intense gravitational field. The closer the clock gets to the event horizon, the more pronounced this effect becomes. For an observer far away, watching the clock approach the black hole, it would appear to tick slower and slower. If they could somehow peer at the clock, they would see events on that clock unfold in agonizing slow motion. The light emitted by the clock would also be stretched to longer wavelengths, a phenomenon known as gravitational redshift, further emphasizing the slowing of time. If the clock were to actually cross the event horizon, from the perspective of the distant observer, it would seem to freeze in time, its light fading into invisibility as it reaches the point of no return. However, for an observer asterisk on that clock, or falling with it towards the black hole, time would feel perfectly normal. Their heart would beat at its usual rhythm, their thoughts would flow at their usual speed. They wouldn't asterisk feel time slowing down. It's only when comparing their experience to that of someone in a weaker gravitational field that the difference becomes apparent. This is the essence of relativity. There is no absolute, universal clock. Time is relative to the observer's motion and their position within a gravitational field. The extreme nature of time dilation near a black hole means that a person falling into one would experience a vastly different passage of time compared to someone safe on Earth. A journey that might feel like mere minutes or hours to the unfortunate traveler could correspond to years, centuries, or even millennia passing for the rest of the universe. This creates a profound disconnect, a cosmic temporal chasm, between the fate of those who venture too close and the ongoing existence of the wider cosmos. It's a stark reminder of how gravity, this fundamental force we often take for granted, can fundamentally alter our perception and experience of reality itself. The very ticking of our existence is, in a sense, a product of our location in the grand gravitational tapestry of the universe. Near a black hole, the very seconds of our lives stretch into an eternity, a silent testament to the universe's profound and gentle manipulation of our most fundamental experience. Accretion disks, the glowing, swirling death throes of matter. Imagine, if you will, a celestial ballet of immense forces. When matter, gas, dust, even stars ventures too close to a black hole, it doesn't simply vanish. Instead, it's caught in the black hole's gravitational embrace, not falling directly in but spiraling inwards. This infalling material forms an accretion disk, a vast, flattened structure that spins around the black hole at incredible speeds. As this matter orbits, friction begins to build. Think of it like rubbing your hands together very, very quickly. They get warm. In an accretion disk, this friction is amplified to an astonishing degree due to the intense gravitational gradients and the sheer velocity of the particles. This friction heats the material to millions, even billions of degrees Celsius, causing it to glow intensely across the electromagnetic spectrum, from radio waves to X-rays and even gamma rays. This is why we can sometimes see black holes, not directly, but by observing the brilliant light emitted by their accretion disks. The inner edge of the disk, closest to the black hole, is where the temperatures are highest and the radiation is most intense. As matter spirals closer, it accelerates, and the gravitational pull becomes overwhelmingly dominant. Particles are stripped from their orbits, stretched and compressed, and eventually, if they cross the event horizon, they are lost to our observable universe. Yet, the disk itself can be a dynamic and complex structure. It's not always a smooth, uniform flow. Magnetic fields play a crucial role, channeling and shaping the plasma, sometimes leading to the expulsion of powerful jets of particles from the poles of the black hole, perpendicular to the disk. These jets, also incredibly energetic and luminous, can extend for vast distances, influencing the surrounding interstellar medium and even the evolution of galaxies. The accretion disk is, in essence, a cosmic engine powered by gravity, converting potential energy into light and heat. It's a testament to the violent, yet ordered, processes that occur in the universe's most extreme environments. The swirling, incandescent disk is the final, brilliant act in the story of matter succumbing to the insatiable pull of a black hole, a spectacular display of physics at its most extreme, a luminous testament to the fundamental forces shaping our cosmos. In the incandescent dance of falling matter, a black hole's presence is revealed in a radiant, fiery embrace. Jets of plasma erupt from the poles of some black holes. Imagine, if you will, the immense gravitational pull of a black hole, a force so profound it bends light and warps the very fabric of spacetime around it. Yet this cosmic maw is not always a silent, passive abyss. In a breathtaking display of power, many black holes, particularly those actively feeding, launch colossal streams of superheated plasma, often traveling at speeds approaching that of light, outward from their polar regions. These are known as relativistic jets. The formation of these jets is a complex and still researched phenomenon, but the prevailing models involve the black hole's accretion disk and its magnetic field. As matter, like stars or gas clouds, spirals inward towards the black hole, it doesn't fall in directly. Instead, it forms a flattened, swirling disk, an accretion disk, where friction heats the material to incredible temperatures, causing it to glow brightly across the electromagnetic spectrum. Within this turbulent disk, powerful magnetic field lines are generated. These magnetic fields become twisted and amplified by the rapid rotation of the disk and the black hole itself. It's within this highly magnetized environment that the magic, or rather the physics, happens. The magnetic field lines, acting like cosmic conductors, channel charged particles, electrons, protons, and other ions from the inner regions of the accretion disk. These particles are accelerated to extraordinary velocities along the magnetic field lines, which are thought to be predominantly aligned with the black hole's spin axis. Imagine them being funneled and then violently ejected, like a cosmic laser beam, from the north and south poles of the black hole. These jets can extend for vast distances, far beyond the confines of the black hole itself, sometimes spanning hundreds of thousands or even millions of light years. They are not uniform streams but can be highly collimated, meaning they remain tightly focused over these immense distances. They are also incredibly energetic, carrying an enormous amount of kinetic energy and contributing significantly to the overall energy budget of their host galaxies. The exact mechanism by which these particles are accelerated to such extreme speeds, and how the magnetic fields maintain their collimation over such vast scales, are still areas of active investigation. Theories suggest various processes, including magnetic reconnection, where twisted magnetic field lines suddenly snap and release their stored energy, and the Blandford-Zenagic process, which proposes that the rotational energy of the black hole itself can be extracted and converted into the kinetic energy of the jets via the magnetic field. These polar jets are not just a spectacle, They play a crucial role in the evolution of galaxies. They can heat the surrounding intergalactic gas, influencing star formation rates and shaping the structure of the cosmic web. In active galactic nuclei, AGN, the luminous centers of some galaxies powered by supermassive black holes, these jets are particularly prominent and can be observed across the universe. They are a testament to the dynamic and often violent nature of the cosmos, revealing that even the most seemingly inescapable gravitational wells can be sources of immense outward energy. They are the black hole's powerful exhale, a cosmic exhalation that shapes its environment. And so, from the deepest gravitational wells, streams of light and matter are flung outwards, painting the cosmos with energetic brushstrokes. Supermassive black holes reside at the center of most galaxies. Imagine, if you will, the vastness of our own Milky Way galaxy, a swirling disk of billions of stars, nebulae, and dust, all held together by an unseen gravitational embrace. And at its very heart, almost like the majestic, silent conductor of this cosmic orchestra, lies a supermassive black hole. This isn't just a small, isolated phenomenon. It's a fundamental architectural feature of galactic structures across the observable universe. The sheer scale is almost incomprehensible. These central behemoths can possess masses ranging from millions to billions of times that of our Sun. They are not merely passive inhabitants. They are active participants in the life and evolution of their host galaxies. The journey to understanding this central truth has been a remarkable one. For a long time, astronomers observed that the stars and gas clouds at the centers of galaxies were moving at incredibly high speeds, far faster than could be explained by the visible matter alone. This suggested the presence of an immense, unseen mass. The most compelling explanation, the one that fits all the observational data, is the existence of a supermassive black hole. These are not the stellar mass black holes, born from the collapse of individual massive stars. Supermassive black holes are a different beast entirely, and their formation remains an active area of research. One prevailing theory suggests that they began as smaller seed black holes, perhaps formed from the very first massive stars in the early universe, or through the direct collapse of vast clouds of gas. These seeds then grew over cosmic time, accreting surrounding gas, dust, and even entire stars. Another significant mechanism for their growth is through mergers. When galaxies collide and merge, their central supermassive black holes often coalesce, combining their masses to form an even larger entity. This process is a key driver in the evolution of galaxies, influencing their shape, size, and star formation rates. The influence of these central engines extends far beyond their immediate vicinity. The supermassive black hole at the center of a galaxy is intimately connected to the galaxy's overall structure and dynamics. The gravitational pull of the black hole influences the orbits of stars and gas clouds, shaping the galactic bulge, and sometimes even the spiral arms. Furthermore, many supermassive black holes are actively feeding, drawing in matter that forms a superheated, rapidly spinning accretion disk. As matter spirals inward, it releases enormous amounts of energy in the form of radiation and powerful jets of particles that can extend thousands, even millions of light years into intergalactic space. These energetic outflows, known as active galactic nuclei, AGN, or quasars when particularly luminous, can profoundly impact the surrounding galaxy. They can heat up or blow away the gas that would otherwise fuel star formation, effectively regulating the growth of the galaxy. In some cases, these outflows can even quench star formation entirely, leading to the formation of red and dead elliptical galaxies. The very existence of galaxies as we observe them, with their diverse morphologies and star populations, is inextricably linked to the presence and activity of these central supermassive black holes. They are not just curiosities, they are fundamental architects, shaping the cosmic landscapes we observe. And so, in the silent, majestic heart of nearly every galaxy, a supermassive black hole orchestrates a cosmic ballet, a silent testament to gravity's ultimate power and the universe's grand design. The Milky Way's supermassive black hole is Sagittarius A. At the very heart of our own celestial home, the Milky Way galaxy, lies a profound and invisible entity, Sagittarius A, often shortened to SGRA. This is not a star, nor a nebula, but a supermassive black hole, a cosmic leviathan whose gravitational pull governs the innermost workings of our galaxy. It is a place of unimaginable density, a point where the very fabric of spacetime is stretched and warped to its absolute limit. For decades, astronomers have meticulously observed the motions of stars and gas clouds swirling around the galactic center, their orbits providing irrefutable evidence of a massive, unseen object. These stars, moving at speeds that defy comprehension, are not simply drifting. They are locked in a gravitational dance with SGRA, their paths tracing the invisible contours of its immense influence. Imagine a cosmic whirlpool where the water is not liquid, but the very essence of space and time, and the central drain is this colossal black hole. The evidence for SGRA has been built over many years, through painstaking observations using powerful telescopes that can peer through the dense dust and gas obscuring the galactic center. We can see stars, like S02, orbiting SGRA at astonishing speeds, some reaching over 14,000 kilometers per second. Their orbits are so precise, so predictable, that they act like cosmic clockwork, revealing the mass and location of the unseen object at the center. From these observations, we know that SGRA has a mass equivalent to about 4 million times that of our Sun, all packed into a region no larger than our solar system. This is a density that defies everyday intuition, a concentration of matter so extreme that it warps spacetime around it, bending the paths of light that pass nearby. The very existence of SGRA at the center of our galaxy is a testament to the fundamental processes that shape cosmic structures. It is believed to have grown over billions of years, likely by accreting gas, dust, and even stars that ventured too close. Mergers with other, smaller black holes may also have contributed to its colossal size. While we cannot directly see the black hole itself, as light cannot escape its event horizon, we can observe its profound effects on its surroundings. The energetic phenomena occurring near SGRA, such as the emission of radio waves and the intense gravitational lensing of background objects, paint a picture of an active and powerful cosmic engine. Understanding SGRA is not just about comprehending our galactic core. It is about understanding the universal principles that govern the formation and evolution of galaxies throughout the cosmos. And so, even at the heart of our own cosmic neighborhood, a profound mystery resides, a silent testament to the universe's grandest forces, reminding us of our small yet connected place within its vast, unfolding story. Black holes warp spacetime, bending light. Imagine the universe not as an empty void, but as a vast, invisible fabric, a tapestry woven from the very essence of existence. This fabric is spacetime, a concept introduced by Albert Einstein in his theory of general relativity. It's a four-dimensional continuum, where 3 dimensions of space are interwoven with the dimension of time. In the absence of any mass or energy, this fabric would be perfectly flat, like a still, calm pond. But when mass and energy are introduced, they create curves and divots in this fabric, much like placing a heavy ball on a stretched rubber sheet. This curvature is what we perceive as gravity. Now consider a black hole. It is an object of immense mass compressed into an infinitesimally small point, or at least, a region so dense that its gravitational pull is overwhelming. This extreme concentration of mass creates an incredibly deep and steep well in the fabric of space-time. It's not just a gentle dimple, it's a profound distortion, a cosmic whirlpool that pulls everything towards its center. Light, which we often think of as traveling in perfectly straight lines, also travels through space-time. And just like any other object moving through this curved fabric, light must follow the contours of space-time. When light from distant stars or galaxies passes near a black hole, it doesn't continue on its original straight path. Instead, the intense curvature of space-time around the black hole forces the light to bend. This bending of light is a direct consequence of gravity, as described by general relativity. It's a phenomenon that has been experimentally verified, most famously during solar eclipses when the light from distant stars passing by the sun, which also warps space-time, is observed to be shifted from its expected position. A black hole, with its vastly greater mass and density, causes an even more dramatic bending of light. The effect can be so profound that light can be bent around a black hole in a complete circle, forming what is known as an Einstein ring, if the alignment is just right. Or, the light can be deflected at such extreme angles that it appears to come from a completely different direction. This is why black holes can act like cosmic lenses, magnifying and distorting the images of objects behind them. The event horizon, the boundary around a black hole beyond which nothing, not even light, can escape, is a direct manifestation of this extreme spacetime warping. At the event horizon, spacetime is curved so severely that all possible paths for light and matter lead inward. It's a one-way street into the heart of the black hole. This bending of light is not just a curious optical illusion. It's a fundamental aspect of how black holes interact with the universe. It's a testament to the profound interconnectedness of mass, energy, spacetime, and gravity. It shows us that the universe is not a static stage upon which events unfold, but a dynamic, malleable entity, shaped and distorted by the very objects it contains. The light we see, the images we form, are all products of this cosmic dance of curvature and motion. The bending of light by a black hole is a silent whisper of the universe's profound geometry. Hawking radiation, black holes slowly evaporate. Imagine, if you will, a concept so profound it challenges our very intuition about the universe's most enigmatic objects. Black holes, those cosmic entities so dense and gravitationally powerful that not even light can escape their grasp, are not, as we might have once thought, eternal. Stephen Hawking, with his brilliant mind and unwavering spirit, proposed a theory that suggests these seemingly invincible celestial bodies are, in fact, subject to a slow, almost imperceptible process of decay. This phenomenon, now known as Hawking radiation, paints a picture of black holes not as ultimate prisons, but as entities that, over unfathomable stretches of time, can indeed fade away. To understand Hawking radiation, we must venture into the quantum realm, a place where the familiar rules of classical physics begin to bend and twist. At the very edge of a black hole, the event horizon, the boundary beyond which escape is impossible, quantum mechanics reveals a fascinating dance of virtual particles. According to quantum field theory, the vacuum of space is not truly empty. Instead, it is a seething, energetic soup of particle-antiparticle pairs that are constantly popping into existence and then annihilating each other almost instantaneously. These are known as virtual particles. They exist for an infinitesimally short period before their energies are exchanged and they cease to be. Now, consider what happens when one of these virtual particle-antiparticle pairs appears right at the event horizon of a black hole. It is a moment of cosmic chance, a quantum lottery. In most instances, the pair will annihilate each other as usual, their fleeting existence ending in a silent whisper. However, on rare occasions, one of the particles in the pair might fall into the black hole, crossing the event horizon, while its partner manages to escape into the vastness of space. This is where the magic, or rather, the physics, truly begins. The particle that falls into the black hole is, in a sense, carrying negative energy relative to an observer far away. This negative energy is effectively absorbed by the black hole, causing its mass to decrease slightly. The particle that escapes, on the other hand, is observed as a real particle being emitted from the vicinity of the black hole. To an outside observer, it appears as if the black hole itself is radiating particles, hence the name Hawking radiation. This process is incredibly slow, especially for stellar mass or supermassive black holes. The rate at which a black hole radiates energy is inversely proportional to its mass. This means that larger black holes radiate much more slowly than smaller ones. For a black hole with the mass of our Sun, it would take an incomprehensibly long time, far longer than the current age of the universe, for it to evaporate completely. Imagine a time scale so vast that the very concept of time, as we understand it, begins to feel like a fleeting moment. However, the implications of this theory are monumental. It suggests that black holes are not permanent features of the cosmos, but temporary ones. Over eons, they will lose mass and energy, eventually diminishing to nothing. This process also has profound implications for the information paradox, a long-standing puzzle in physics. The paradox arises from the conflict between general relativity, which suggests that information falling into a black hole is lost forever, and quantum mechanics, which insists that information cannot be destroyed. Hawking radiation offers a potential resolution, suggesting that as a black hole evaporates, it might slowly release the information it has consumed, albeit in a scrambled and thermalized form. The energy emitted as Hawking radiation is thermal, meaning it has a characteristic temperature. This temperature is also inversely proportional to the black hole's mass. Smaller black holes are hotter and radiate more intensely, while larger black holes are colder and radiate more feebly. If a black hole were to become incredibly small, its temperature would rise dramatically, and it would evaporate at an accelerating rate, culminating in a final, energetic burst. This gradual dissipation, this slow surrender of mass and energy, transforms our perception of black holes from absolute cosmic voids to entities that, in their own silent way, participate in the grand cosmic cycle of creation and dissipation. It is a testament to the interconnectedness of all things, a reminder that even the most seemingly immutable forces in the universe are subject to change, to a gentle, albeit incredibly slow, transformation. And in this slow evaporation, we find a quiet echo of our own impermanence, a cosmic perspective that even the most powerful forces eventually yield to the passage of time. The information paradox: what happens to information that falls in? Imagine, if you will, a meticulously crafted book, its pages filled with the history of a civilization, the intricacies of its art, the whispers of its poetry. Now picture this book, a vessel of pure information tumbling towards the abyss of a black hole. According to the laws of quantum mechanics, information, once it exists, can never truly be destroyed. It may be scrambled, it may be transformed, but its fundamental essence, its very existence, should persist. Yet classical general relativity, our current understanding of gravity and black holes, suggests something profoundly different. When matter, and with it its information, crosses the event horizon, it seems to vanish from our observable universe, destined to be crushed into the singularity at the heart of the black hole. This creates a profound conflict, a paradox that has puzzled physicists for decades. If information is lost within a black hole, then quantum mechanics, one of the most successful theories ever devised, must be fundamentally incomplete or incorrect in these extreme environments. One of the key figures in grappling with this paradox was Stephen Hawking. His groundbreaking work on Hawking radiation suggested that black holes are not entirely black, but rather slowly emit particles over vast timescales, a process by which they eventually evaporate. This evaporation, however, was initially thought to be purely thermal, meaning the emitted particles carry no specific information about what fell into the black hole. It's akin to burning that book. The ashes and smoke are still there, but the specific words, the stories, are gone, replaced by a generic thermal signature. This thermal emission implied a loss of information, a direct violation of quantum principles. This apparent contradiction has led to a multitude of theoretical proposals, each attempting to reconcile the seemingly incompatible tenets of general relativity and quantum mechanics. One prominent idea is that the information isn't truly lost, but rather encoded in the Hawking radiation itself, albeit in an incredibly subtle and scrambled form. Perhaps the particles emitted carry faint echoes of the infalling matter, like a faint imprint on a cosmic breeze. Think of it as the ashes and smoke still retaining a ghost of the original book's content, but requiring an impossibly complex deciphering process to retrieve. This concept is often referred to as the holographic principle, suggesting that the information contained within a volume of space can be represented on its boundary, much like a hologram projects a 3D image from a 2D surface. In this view, the surface of the black hole, or perhaps the event horizon itself, acts as a kind of cosmic hard drive, storing the information of everything that has fallen in. Another possibility is that the information is somehow preserved within the singularity itself. While our current understanding of physics breaks down at this point, it's conceivable that a more complete theory of quantum gravity might reveal a mechanism for information storage or transformation that we cannot yet comprehend. Perhaps the singularity is not a true endpoint, but a gateway to another region of space-time, or a state where information can exist in a form we haven't imagined. This is a realm of pure speculation, but it highlights the profound limitations of our current knowledge when confronting the extreme conditions around a black hole. The quest to resolve the information paradox is not merely an academic exercise for theoretical physicists. It represents a fundamental challenge to our understanding of the universe at its most basic level. It forces us to confront the very nature of reality, the limits of our knowledge, and the deep, interconnected fabric of space-time and quantum mechanics. It is a testament to the enduring mysteries that lie hidden within the cosmos, urging us to look deeper, to question our assumptions, and to continue our patient exploration of the universe's most profound secrets. And so, the whispered stories of the lost, like faint starlight, may still hold their truth, carried on the silent currents of existence, even as the darkness deepens. Black holes are born from the death of massive stars. Imagine, if you will, a star many times larger than our own sun, a celestial titan burning with incredible brilliance and immense power. For millions, perhaps even billions of years, these colossal stars engage in a cosmic ballet of nuclear fusion at their very core. Hydrogen atoms are squeezed together, forced to meld into helium, releasing an astounding amount of energy that pushes outward, counteracting the relentless inward pull of gravity. This delicate equilibrium, this constant push and pull, is what sustains a star, allowing it to shine and radiate light and heat across the vastness of space. But even the most magnificent of stars cannot burn forever. Eventually, the nuclear fuel at its core begins to dwindle. As the hydrogen is exhausted, the star begins to fuse heavier elements, moving through helium, carbon, oxygen, and so on, up the periodic table. Each stage of fusion releases less energy than the last, and the outward pressure fighting against gravity weakens. For stars that are exceptionally massive, this process continues until iron is formed. Iron is a peculiar element in this context, because fusing iron doesn't release energy. Instead, it consumes it. This is the critical turning point. When the core of a massive star becomes predominantly iron, fusion ceases. The outward pressure that had been holding the star aloft vanishes almost instantaneously. Gravity, unchecked, takes over with cataclysmic force. The core collapses inward with unimaginable speed, a fraction of a second's descent that triggers a shockwave. This shockwave propagates outward through the star's outer layers, causing a spectacular explosion known as a supernova. This supernova is one of the most energetic events in the universe, briefly outshining entire galaxies. However, what remains of the star's core after this violent expulsion depends entirely on its initial mass. If the remaining core is between about 1.4 and 3 times the mass of our Sun, it will collapse into an incredibly dense object called a neutron star. But for stars that were even more massive, those that began their lives with more than, say, 20 to 25 times the mass of our Sun, the collapse continues. Gravity is so overwhelmingly powerful that it crushes the core beyond the density of a neutron star. The matter is squeezed into an infinitesimally small point, or at least, a point so small that our current understanding of physics struggles to describe it. This is the birth of a stellar mass black hole. The immense gravitational pull of this collapsed core becomes so strong that nothing, not even light, can escape its grasp. The boundary beyond which escape is impossible is known as the event horizon. This is the point of no return. So in essence, these cosmic behemoths, after a life of dazzling brilliance, end their existence not in a gentle fade, but in a violent, transformative collapse that births one of the most enigmatic objects in the universe. It is a testament to the extreme forces at play in the cosmos, a dramatic end that ushers in a new, profoundly different kind of existence. The very fabric of spacetime is warped and contorted around this dense remnant, creating a region of ultimate gravitational power. The death of a star, for the most massive among them, is not an end, but a transformation into something far more potent and mysterious. In the fiery demise of a giant, gravity claims its ultimate prize, birthing a silent sentinel that warps the very weave of existence. Neutron stars are the precursors to some black holes. Imagine the most extreme stellar corpse you can conceive, and then imagine something even more dense, more compact, more utterly alien. That, my friends, is the neutron star. These celestial bodies are the remnants of stars far more massive than our own Sun, stars that have reached the end of their fiery lives and collapsed under their own immense gravity. When such a star exhausts its nuclear fuel, it can no longer support itself against the relentless inward pull. For stars in a specific mass range, typically between about 8 and 20 times the mass of our Sun, this collapse doesn't quite lead to a black hole, not immediately anyway. Instead, the core implodes, crushing protons and electrons together with such unimaginable force that they fuse to form neutrons. This process, called neutronization, creates a substance so dense that a single teaspoon of it would weigh more than all the mountains on Earth combined. The collapse is halted by a quantum mechanical pressure called neutron degeneracy pressure, a force arising from the Pauli exclusion principle, which prevents neutrons from occupying the same quantum state. This pressure counteracts gravity, forming a stable, albeit incredibly exotic stellar object, a neutron star. These stars are astonishingly small for their mass, often only about 20 kilometers in diameter, yet they pack in more mass than our Sun. They spin at incredible speeds, sometimes hundreds of times per second, and possess magnetic fields billions of times stronger than Earth's. But here's where the precursor aspect comes in. While neutron stars are stable in themselves, they are precariously balanced. If a neutron star were to gain additional mass, perhaps by accreting material from a companion star or through a merger with another compact object, it could tip over the edge. Neutron degeneracy pressure has its limits. Once a neutron star exceeds a certain critical mass, known as the Tolman-Oppenheimer-Volkoff limit, around 2 to 3 solar masses, even this quantum force can no longer resist gravity's crushing embrace. The star will collapse further, overcoming all known physical barriers, and its core will shrink down to an infinitely small point, a singularity. At this point, an event horizon will form, and the neutron star will have transformed into a black hole. So in a sense, many black holes are born from the dramatic, explosive death of a star, followed by the compact, exotic existence of a neutron star, which then undergoes a final, ultimate collapse to become a black hole. They are intermediate stages, cosmic stepping stones on the path from a colossal star to the ultimate gravitational abyss. The neutron star, a monument to stellar collapse, holds the potential for a final, profound transformation into the silent abyss. Stellar mass black holes are scattered throughout galaxies. Imagine, if you will, the vastness of our own Milky Way galaxy, a swirling disk of stars, gas, and dust, stretching across hundreds of thousands of light years. Within this immense cosmic tapestry, there exist countless invisible entities, remnants of stellar evolution, that profoundly influence their surroundings. These are the stellar mass black holes, and they are not rare curiosities, but rather an integral and widespread component of galactic architecture. A stellar mass black hole is born when a star, significantly more massive than our Sun, exhausts its nuclear fuel. In its final moments, it collapses under its own immense gravity. This catastrophic implosion triggers a supernova explosion, a brilliant, violent burst of light that can outshine an entire galaxy for a brief period. What remains after this cosmic demise, if the core is massive enough, is a stellar mass black hole. These objects typically range from about 3 to a few dozen times the mass of our Sun. While they are stellar mass, their gravitational pull is anything but small. Their density is so extreme that nothing, not even light itself, can escape their grasp once it crosses a certain boundary known as the event horizon. The sheer number of these black holes within a galaxy is staggering. For every 1,000 or so stars in our Milky Way, it's estimated there might be one stellar mass black hole. This means there could be millions, even billions of these enigmatic objects silently orbiting within our galactic home. They are not confined to specific regions, but are distributed throughout the galactic disk and even into the halo, the spherical region surrounding the galaxy. Think of them as the unseen anchors, the silent gravitational wells that contribute to the overall dynamics and structure of the galaxy. Their presence influences the orbits of nearby stars, sometimes creating peculiar stellar streams or causing stars to accelerate dramatically. While we cannot see them directly, their gravitational influence on visible matter provides irrefutable evidence of their existence. Astronomers detect them by observing the behavior of companion stars, which may orbit an unseen object at high speeds, or by witnessing the intense X-ray radiation emitted when matter is pulled from a companion star onto the black hole. This process, known as accretion, heats the infalling material to incredibly high temperatures, causing it to glow brightly in X-rays. The distribution of these stellar mass black holes is a testament to the universal nature of stellar evolution. Every galaxy, from the grand spirals to the irregular dwarfs, is likely populated by these stellar remnants. They are the silent, invisible children of massive stars, scattered like cosmic dust across the grand stage of the universe, each a testament to the cyclical nature of creation and destruction. Their pervasive presence underscores the idea that even in the unseen, the universe is teeming with activity and complex gravitational interactions that shape the grand cosmic ballet. Like quiet whispers in the cosmic wind, these stellar remnants are woven into the very fabric of galactic existence. Intermediate-mass black holes remain elusive. For decades, our understanding of black holes has been dominated by two well-defined categories: stellar mass black holes, born from the collapse of individual stars, and supermassive black holes, residing at the hearts of galaxies. Stellar mass black holes typically range from a few times to a few dozen times the mass of our Sun. They are relatively common, scattered throughout galaxies like cosmic embers left from stellar fires. At the other extreme, supermassive black holes can possess masses of millions, even billions of suns. Their presence is a defining feature of galactic centers, influencing the dynamics and evolution of entire galaxies. The existence of these two distinct populations, separated by such a vast gulf in mass, has long been a cornerstone of black hole astrophysics. However, as our observational capabilities have grown and our theoretical models have become more sophisticated, a curious gap has emerged in this otherwise tidy classification. This gap lies in the realm of intermediate-mass black holes, or IMBHs. IMBHs, as their name suggests, are theorized to bridge the mass range between their smaller stellar cousins and their colossal galactic counterparts. Their predicted masses would fall somewhere between 100 and 100,000 solar masses, a substantial range that hints at fascinating formation mechanisms and potentially unique roles in the cosmic landscape. The idea of IMBHs is not new. Astronomers have hypothesized their existence for many years, driven by theoretical considerations and tantalizing, albeit often ambiguous, observational hints. If they exist, they could represent crucial stepping stones in the formation of supermassive black holes, perhaps forming in the dense cores of ancient star clusters, and then merging over cosmic timescales to grow to immense sizes. Alternatively, they might form through different processes entirely, such as the direct collapse of massive gas clouds in the early universe or runaway collisions of stars in extremely dense stellar environments. The challenge, however, has been their detection. Unlike stellar mass black holes, which are often found in binary systems with visible stars, allowing astronomers to infer their presence through gravitational influence and X-ray emissions, or supermassive black holes, whose gravitational pull dominates entire galactic nuclei, IMBHs are more difficult to pinpoint. They are too massive to be easily formed from single stellar collapses, yet not massive enough to dominate the centers of large galaxies in a way that's immediately obvious. They might reside in the cores of smaller galaxies, in the dense hearts of globular clusters, or perhaps in regions where star formation is particularly intense. Detecting an IMBH requires observing its gravitational effects on its surroundings. This could involve monitoring the orbits of stars in a dense star cluster, looking for unexpectedly high velocities that suggest the presence of a massive, unseen object. Another approach is to search for signs of accretion, where gas and dust are drawn towards the black hole, heating up and emitting X-rays. However, distinguishing the X-ray signature of a potential IMBH from other energetic astrophysical phenomena, like neutron stars or active star-forming regions, can be incredibly challenging. Furthermore, The very environments where IMBHs are expected to exist, such as the chaotic cores of globular clusters, are already bustling with complex interactions and powerful radiation sources, making the isolation of an IMBH signal a formidable task. Despite these difficulties, there have been several compelling candidates for IMBHs. Some ultraluminous X-ray sources, ULXs, have been observed, which are X-ray emitters far brighter than typical stellar mass black holes in binary systems. Some of these ULXs are thought to reside in dwarf galaxies or globular clusters, environments where IMBHs are predicted. The unusually high luminosity of these ULXs suggests that their central black holes might be more massive than stellar mass black holes, or perhaps they are accreting matter at unusually high rates. Another promising avenue involves observations of the centers of dwarf galaxies. These smaller galaxies are thought to be less evolved than larger galaxies and may have retained the conditions necessary for IMBH formation and survival. Some dwarf galaxies have shown evidence of compact, massive objects at their centers that are too small to be supermassive black holes, but too large to be stellar mass black holes. The search for IMBHs is an ongoing frontier in astrophysics, a quest to fill a significant gap in our cosmic census of black holes. Their discovery and characterization would not only refine our understanding of black hole evolution, but could also shed light on the formation of the first galaxies and the intricate processes that govern the growth of the largest structures in the universe. The elusive nature of intermediate mass black holes underscores the vastness of the unknown that still surrounds these enigmatic objects, a testament to the ongoing journey of cosmic discovery. And so, the universe holds its breath, waiting for the definitive whisper of these intermediate giants, a silent testament to the unseen architecture of the cosmos. Supermassive black holes grow by consuming matter and merging. Imagine, if you will, the immense, silent architects of galactic structures, supermassive black holes. These behemoths residing at the heart of most galaxies are not static entities. They are dynamic, ever-growing forces, their expansion fueled by two primary cosmic processes: the relentless consumption of surrounding matter and the profound, universe-altering event of merging with other black holes. Think of it as a celestial appetite, a hunger that shapes the very galaxies they inhabit. The process of accretion, the slow or sometimes rapid devouring of gas, dust, stars, and even other, smaller black holes, is a fundamental mechanism for their growth. As matter spirals inwards, drawn by the black hole's immense gravitational pull, it forms an accretion disk. This disk becomes incredibly hot due to friction and gravitational forces, often blazing with intense radiation, making these central regions some of the brightest objects in the universe, known as active galactic nuclei or quasars. This infalling material over eons adds mass to the central black hole, increasing its size and gravitational influence. But accretion is not the only path to growth. Black holes, especially supermassive ones, are also capable of merging. When galaxies collide, their central supermassive black holes are eventually drawn together. This is a cataclysmic event, a cosmic ballet of unimaginable power. As they spiral towards each other, they warp space-time, sending ripples or gravitational waves through the universe. The final moments before a merger are a spectacle of extreme physics, a dance of destruction and creation. When they finally collide, they form a single, larger black hole, an entity even more massive and influential than its predecessors. This process of merging is a significant contributor to the growth of supermassive black holes, particularly in the early universe when galaxy collisions were more frequent. These mergers are not just about adding mass. They can also trigger bursts of star formation, and dramatically alter the structure and evolution of the galaxies involved. The seeds of these colossal entities are thought to have been present even in the nascent universe, growing rapidly through a combination of gas accretion and mergers in the dense environments of early galaxies. The sheer scale of these processes is difficult to comprehend. A single supermassive black hole can have a mass millions or even billions of times that of our Sun. The energy released during accretion and mergers is staggering, influencing the surrounding interstellar medium, pushing gas outwards, and shaping the distribution of matter on vast scales. These growing giants are not just passive observers of cosmic evolution. They are active participants, their growth intimately tied to the life and death of stars, the formation of galaxies, and the very structure of the cosmos. The continuous influx of matter and the dramatic events of mergers ensure that these central engines of galaxies remain powerful forces, their influence extending far beyond their immediate vicinity, shaping the grand cosmic tapestry in ways we are only beginning to fully understand. The universe, in its vastness, is a testament to these ongoing processes of growth and transformation, with supermassive black holes standing as enduring monuments to the power of gravity and the relentless march of cosmic time. Their hunger is eternal, their mergers are profound, and their growth is a fundamental narrative of the universe's unfolding story. And so these silent, insatiable giants grow, a testament to the universe's constant, patient, and awe-inspiring process of becoming. Galactic evolution is influenced by supermassive black holes. At the heart of almost every large galaxy, like our own Milky Way, lies a supermassive black hole. These behemoths, millions or even billions of times the mass of our Sun, are not merely passive inhabitants of galactic centers. Instead, they play an active and profound role in shaping the very evolution of the galaxies they reside within. This influence, often referred to as feedback, is a complex interplay of energy and matter that can dramatically alter the birth rate of stars, the distribution of gas, and ultimately, the overall structure and appearance of a galaxy over cosmic timescales. Imagine a galaxy as a vast, intricate ecosystem. Within this ecosystem, stars are born, live, and die, releasing energy and heavy elements. Gas and dust clouds drift and swirl, providing the raw material for new star formation. Supermassive black holes, through a process called accretion, are constantly drawing in surrounding matter. As this matter spirals towards the black hole, it forms an accretion disk, a superheated, rapidly rotating structure. The intense gravitational forces and friction within this disk cause it to emit enormous amounts of radiation across the electromagnetic spectrum, from radio waves to X-rays. But the influence of a supermassive black hole extends far beyond the immediate vicinity of its accretion disk. Many supermassive black holes are also observed to launch powerful, collimated jets of plasma that can extend for hundreds of thousands, or even millions, of light years into intergalactic space. These jets are thought to be powered by the black hole's rotation and the magnetic fields within the accretion disk. It is this energetic output, the radiation from the accretion disk and the momentum carried by the jets, that constitutes the feedback mechanism. This feedback can have a dual effect on the galaxy. On one hand, the intense radiation and outflows can compress gas clouds, triggering bursts of star formation. This is known as positive feedback, where the black hole's activity can lead to a more rapid growth of the galaxy. However, the more significant and widely recognized effect is negative feedback. The immense energy and momentum injected into the galaxy by the black hole can heat up or expel the surrounding gas. This gas is the fuel for star formation. If the gas is heated to very high temperatures, it can become too diffuse to collapse and form new stars. If it is expelled entirely from the galaxy, it is permanently lost as a source of future star formation. In this way, supermassive black holes can effectively quench star formation in their host galaxies, preventing them from growing indefinitely and leading to the formation of red, quiescent galaxies that are dominated by older stars. This process is particularly important in understanding the observed diversity of galaxies. Galaxies that are actively feeding their central black holes tend to be more luminous and may experience rapid starbursts. Conversely, galaxies where the black hole's feedback has successfully suppressed star formation become less active, with fewer young stars and a more stable, evolved population. The balance between accretion onto the black hole and the subsequent feedback process is a critical factor in determining whether a galaxy will continue to form stars or become a dormant, red giant. Furthermore, the growth of supermassive black holes and their host galaxies appear to be closely linked. Observations show a correlation between the mass of a supermassive black hole and the properties of its host galaxy, such as the mass of its stellar bulge. This suggests a co-evolutionary relationship, where the black hole and the galaxy grow together, influencing each other's development. Mergers between galaxies are also thought to play a role, as they can funnel large amounts of gas towards the central black hole, triggering intense activity and potentially leading to the growth of both the black hole and the galaxy. The study of supermassive black hole feedback is a crucial area of modern astrophysics, as it helps us to explain why galaxies look the way they do and how they have evolved over billions of years. It reveals that these seemingly inert objects are, in fact, dynamic engines that play a vital role in the cosmic ballet of galactic formation and evolution. And so, the silent giants at galactic cores are not just observers, but sculptors of cosmic architecture. The cosmic web may be structured by black hole activity. Imagine the grandest, most intricate tapestry you can conceive. Now, expand that image to encompass the entirety of existence, stretching across billions of light years. This is the cosmic web, a vast, filamentary network of galaxies, gas, and dark matter, interspersed with immense voids. For a long time, astronomers pondered what forces sculpted this colossal structure, what cosmic architect drew these luminous threads across the dark canvas of space. While gravity, in its relentless pull, is undoubtedly the primary sculptor, the subtle yet profound influence of black holes, particularly their supermassive cousins dwelling at the heart of galaxies, is increasingly understood to be a crucial element in this grand design. These galactic behemoths are not merely passive inhabitants of their galactic cores. They are active participants, shaping the very environments in which they reside, and by extension, influencing the larger structure of the cosmic web. The process begins with the growth of supermassive black holes. As galaxies merge, their central black holes often coalesce, growing larger and more powerful. These growing black holes are surrounded by accretion disks, swirling disks of gas and dust that are heated to extreme temperatures by the immense gravitational forces. This superheated material emits prodigious amounts of radiation across the electromagnetic spectrum, from radio waves to X-rays. This intense radiation, along with powerful outflows of charged particles, creates what are known as active galactic nuclei, or AGN. These AGN can exert enormous pressure on the surrounding intergalactic medium, the tenuous gas that fills the space between galaxies. This pressure can have a profound effect on the formation and evolution of galaxies within the cosmic web. AGN outflows can heat and expel gas from galaxies, preventing it from cooling and collapsing to form new stars. This process, known as feedback, can regulate the rate at which galaxies grow and can even quench star formation altogether in some galaxies. By controlling the influx of gas into galaxies, AGN feedback indirectly influences the density of galaxies within the filaments of the cosmic web. Regions with more active supermassive black holes might experience less gas accumulation, leading to fewer, or less vigorously star-forming, galaxies within their vicinity. Conversely, in regions where AGN activity is less pronounced, gas may be allowed to accumulate more freely, fostering the growth of more massive galaxies and potentially denser knots within the cosmic web. Furthermore, the sheer energy injected by AGN can influence the distribution of dark matter, the invisible scaffolding upon which the cosmic web is built. While dark matter itself does not interact with radiation, its gravitational influence is paramount. By altering the distribution of baryonic matter, normal matter, AGN can indirectly affect the gravitational potential wells that dark matter occupies, subtly nudging and shaping the large-scale structure. The powerful jets emanating from some AGN can also push through the intergalactic medium, creating cavities and shockwaves that can influence the flow of gas over vast distances, potentially reinforcing or even creating new pathways within the cosmic web's filamentary structure. Consider the immense voids that punctuate the cosmic web. These are regions largely devoid of galaxies. While gravity naturally leads to the clumping of matter, the active role of supermassive black holes might play a part in maintaining and even expanding these vast emptinesses. By continuously pushing gas and energy outwards, AGN could be actively preventing matter from accumulating in certain regions, thereby contributing to the formation and persistence of these cosmic voids. The interplay between the gravitational pull of dark matter and the energetic expulsion by black holes creates a dynamic equilibrium that defines the cosmic web's intricate architecture. The very filaments that connect galaxies and the voids that separate them are, in part, a testament to the ceaseless activity of these enigmatic celestial objects. The cosmic web is not a static snapshot, but a constantly evolving entity. The growth and merging of galaxies, the fueling of their central black holes, and the subsequent energetic feedback are all part of a grand, ongoing cosmic ballet. Understanding this complex interplay is crucial for a complete picture of cosmic structure formation. The seemingly empty space between galaxies is not truly empty. It is filled with diffuse gas that is being stirred and shaped by the powerful forces emanating from the universe's most energetic engines. The profound influence of black holes extends far beyond their immediate galactic neighborhoods, reaching out to orchestrate the very fabric of the cosmos on the grandest scales imaginable, painting the universe with threads of light and shadow. The intricate patterns of the cosmos are whispered into existence by the quiet power of slumbering giants. Gravitational waves reveal the dance of merging black holes. Imagine the universe not as a static backdrop, but as a vast, dynamic tapestry woven from the very fabric of space-time. Now, picture two incredibly massive objects, like black holes, spiraling towards each other, their immense gravitational forces locked in an intricate cosmic ballet. As they draw closer, their very existence warps and distorts this space-time tapestry around them. This distortion isn't just a static bend. It's a ripple, a tremor, a wave that propagates outwards at the speed of light. These are gravitational waves, the universe's most profound whispers, carrying news of the most cataclysmic events. For decades, these waves were purely theoretical, predicted by Einstein's general relativity, but so incredibly faint that detecting them seemed an almost impossible dream. The slightest tremor on Earth, a passing truck, Even the hum of our own bodies could easily drown out these celestial whispers. Yet, with extraordinary ingenuity and patience, scientists have built instruments like LIGO and Virgo designed to be exquisitely sensitive, capable of detecting these infinitesimal distortions. These detectors, essentially colossal rulers made of light, use lasers to measure the precise distances between mirrors miles apart. When a gravitational wave passes through, it minutely stretches and compresses the very space between these mirrors, creating a detectable difference. And what these sensitive ears have begun to hear is astonishing. They've detected the symphony of merging black holes, the final, violent embrace of two cosmic titans. We've heard the thunderous collision of stellar-mass black holes, remnants of exploded stars, hurtling towards each other, their masses combining to form a single, larger black hole. We've even begun to detect the echoes of supermassive black holes, the giants at the hearts of galaxies, engaging in their own slow, majestic dance, their mergers shaping the very evolution of the cosmos. Each detected wave is a snapshot, a unique signature telling us about the masses of the merging objects, their speeds, their directions, and the very nature of gravity under its most extreme conditions. It's like listening to the universe tell its own story, a story written not in light, but in the very curvature of existence. These waves aren't just curiosities. They are windows into phenomena that are otherwise invisible, allowing us to probe the darkest corners of the universe and the most extreme physical environments. They confirm our understanding of gravity in ways that light alone cannot, pushing the boundaries of our knowledge and opening up entirely new avenues of astronomical observation. The universe, it turns out, is not silent. It sings with the vibrations of its most powerful events, and we are finally learning to listen. In the silent hum of existence, the universe whispers its most powerful secrets through the rippling dance of merging worlds. Black holes distort the fabric of reality. Imagine the universe not as a vast, empty stage, but as a flexible, yielding sheet. This is the concept of space-time, a four-dimensional tapestry woven from 3 dimensions of space and 1 dimension of time. It's the fundamental framework within which all events unfold. Now, picture placing a bowling ball onto this sheet. The sheet would sag, creating a dip around the ball. This dip, this curvature, is what we perceive as gravity. The more massive an object, the deeper the dip it creates and the stronger its gravitational pull. Black holes, however, are not mere bowling balls. They are infinitely dense points of matter, representing the ultimate extreme of this gravitational warping. Their mass is so concentrated, their gravitational influence so profound, that they don't just create a dip, they create an abyss, a tear in the very fabric of space-time. This distortion is so severe that light, the fastest thing in the universe, cannot escape its clutches once it crosses a certain boundary. This boundary, known as the event horizon, is not a physical surface, but rather a conceptual one, a threshold beyond which the curvature of spacetime becomes so extreme that all paths lead inward, towards the singularity at the black hole's heart. The warping effect extends far beyond the event horizon, influencing the trajectories of stars and gas clouds, bending the paths of light from distant galaxies, and even affecting the flow of time itself. Near a black hole, time slows down relative to an observer far away, a phenomenon known as gravitational time dilation. This extreme distortion of spacetime is not just a theoretical curiosity. It's a fundamental aspect of how black holes interact with their cosmic surroundings, shaping the structure and dynamics of galaxies and the universe as a whole. They are not simply objects within spacetime. They are architects of it, their immense gravity sculpting the very dimensions in which we exist. In the silent, vast theater of existence, black holes etch their profound curvature, reminding us that reality itself bends to the weight of profound presence. Our universe may contain more black holes than we can currently detect. The cosmos is an unimaginably vast stage, and the players upon it, the stars and galaxies, are often what capture our immediate attention. Yet, lurking in the shadows, or perhaps more accurately, in the profound absence of light, are black holes, and the current census of these enigmatic objects is likely a significant undercount. We have identified a substantial population of stellar mass black holes, those born from the collapse of individual massive stars, and we have a growing understanding of the supermassive black holes that anchor galactic centers. However, the universe is a place of staggering complexity, and the processes by which black holes form, evolve, and interact are far from fully understood. Consider, for instance, the intermediate mass black holes, a hypothesized class of black holes with masses between stellar mass and supermassive. Their existence is supported by indirect evidence, such as the unusual brightness of certain globular clusters or the peculiar behavior of some active galactic nuclei, but direct detection has proven exceptionally challenging. These objects might form through the merger of stellar mass black holes in dense stellar environments, or perhaps through the direct collapse of massive gas clouds in the early universe. If they exist in significant numbers, they would represent a crucial missing link in our understanding of black hole evolution, bridging the gap between the small and the colossal. Furthermore, the very nature of black holes makes them inherently difficult to observe. They do not emit light, so our primary means of detecting celestial objects is rendered useless. We infer their presence through their gravitational influence on surrounding matter and light. This means that black holes that are isolated, or those whose gravitational pull is not actively interacting with a nearby star or gas cloud, can remain invisible to our current observational techniques. Imagine a lone wanderer in the vastness of space, its immense gravity affecting nothing observable. Such objects could be scattered throughout interstellar and intergalactic space, their presence only hinted at by subtle distortions in the cosmic background radiation or the gravitational lensing of distant galaxies. The ongoing advancements in gravitational wave astronomy are opening a new window onto the universe, allowing us to detect the ripples in spacetime caused by the mergers of black holes. This technology is already revealing a population of black holes that were previously unknown, some with masses that challenge our existing stellar evolution models. As these observatories become more sensitive and more widespread, they are likely to uncover an ever larger number of black hole mergers, and by extension, a greater number of black holes themselves. The hunt for dark matter, another pervasive cosmic mystery, also hints at the potential for unseen gravitational entities. While black holes are not dark matter, their existence in vast, undetected numbers could contribute to the gravitational dynamics we observe in galaxies and galaxy clusters. The current estimates of the number of black holes are based on our understanding of stellar populations and galaxy formation, but these models are themselves incomplete. The universe is a dynamic and evolving entity, and our understanding is constantly being refined by new discoveries. It is entirely plausible that the true number of black holes, from the smallest stellar remnants to the giants at galactic cores, and perhaps even exotic forms we haven't yet conceived of, far exceeds our current estimates, making the cosmos a far more populated place with these gravitational titans than we can presently comprehend. In the quiet expanse, unseen titans may far outnumber those we know, their gravity a silent symphony in the cosmic dark. The study of black holes pushes the boundaries of physics. Our current understanding of the universe is built upon two remarkable pillars: Einstein's theory of general relativity, which describes gravity and the large-scale structure of spacetime, and quantum mechanics, which governs the behavior of matter and energy at the smallest scales. These theories have been incredibly successful in their respective domains, explaining phenomena from the orbits of planets to the interactions of subatomic particles. However, when we turn our attention to black holes, these two seemingly disparate frameworks begin to clash, revealing the limitations of our current knowledge. At the heart of a black hole lies a singularity, a point of infinite density and zero volume. According to general relativity, this is where spacetime itself ends, and the laws of physics as we know them break down. Yet, quantum mechanics suggests that such infinities are often smoothed out by quantum effects. The challenge lies in reconciling these two perspectives. How can we describe what happens at the singularity if our theories are incompatible? This is where the quest for a unified theory of quantum gravity truly begins. Physicists are exploring various avenues, such as string theory and loop quantum gravity, attempting to weave together the fabric of spacetime with the probabilistic nature of quantum particles. Consider the event horizon, the boundary beyond which nothing, not even light, can escape. General relativity describes this as a smooth, predictable surface, but quantum mechanics hints at a more complex reality, perhaps involving quantum fluctuations and a fuzzy, uncertain edge. The information paradox, a profound puzzle, further highlights this tension. Quantum mechanics dictates that information can never be truly lost, yet it appears that anything falling into a black hole, including the information it carries, is irrevocably gone. Resolving this paradox requires a deeper understanding of how gravity and quantum mechanics interact at the most fundamental level. The study of black holes forces us to confront phenomena that defy our everyday intuition. The extreme warping of spacetime, the immense gravitational forces, and the potential for exotic quantum effects all push the very limits of our conceptual frameworks. It's like trying to understand a three-dimensional object using only two-dimensional tools. Something crucial is missing. The ongoing research into black holes is not merely an academic exercise. It is a vital step in our quest for a more complete and accurate description of reality. By probing these enigmatic cosmic objects, we are not just learning about black holes, but about the fundamental nature of space, time, gravity, and the very fabric of existence. The equations we write, the experiments we conceive, and the theories we propose are all attempts to bridge the chasm between the cosmic and the quantum, between the immense and the infinitesimal, all in the pursuit of a deeper, more unified understanding of the universe. It is in these extreme environments that the most profound insights are often found, revealing the universe's secrets in ways we could never have imagined. In the crucible of black holes, our physics is tested, revealing the universe's profound and elegant, yet incomplete song. Black holes are natural laboratories for extreme physics. Imagine, if you will, a place where the very rules of reality are stretched, twisted, and tested to their absolute limits. This is precisely what a black hole offers us, not a place of destruction, but a profound, albeit harsh, laboratory for understanding the most fundamental forces in the cosmos. Within these enigmatic entities, conditions are created that we can only dream of replicating here on Earth. The immense gravitational pull of a black hole, for instance, is so powerful that it warps spacetime itself, creating a curvature that dictates the paths of light and matter in ways that defy our everyday intuition. This warping is not just a theoretical curiosity. It's a tangible effect that we can observe and measure, providing crucial data for refining our theories of gravity, particularly Einstein's general relativity. General relativity predicts the existence of black holes and their extraordinary properties, but it is in the extreme environment of a black hole that these predictions can be most rigorously tested. For example, the phenomenon of gravitational lensing, where light from distant objects is bent around a massive object like a black hole, allows us to see further into the universe and to verify the precise way in which mass curves space-time. The closer you get to a black hole, the more pronounced this effect becomes, offering a gradient of gravitational influence that is impossible to recreate in any terrestrial setting. Furthermore, the immense densities and energies involved in the formation and existence of black holes provide a unique arena for studying quantum mechanics in conjunction with gravity. This is a frontier of physics known as quantum gravity, a field that seeks to unify the two pillars of modern physics that currently seem incompatible: the large-scale, smooth fabric of spacetime described by general relativity, and the discrete, probabilistic nature of quantum mechanics. Black holes, with their singularities where density is theoretically infinite and spacetime curvature is extreme, are thought to be the very places where these two theories must meet. The study of phenomena like Hawking radiation, the theoretical emission of particles from black holes, is a direct consequence of attempting to reconcile quantum mechanics with the intense gravitational fields near the event horizon. This radiation, though incredibly faint for astrophysical black holes, suggests that black holes are not entirely black and that they slowly lose mass over vast timescales, a concept that has profound implications for our understanding of entropy and information in the universe. The accretion disks that form around many black holes are also incredibly energetic environments. As matter spirals into a black hole, it is heated to millions of degrees due to friction and compression, emitting intense radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. Studying this radiation allows us to probe the physics of plasma under extreme conditions, the behavior of matter in powerful magnetic fields, and the processes by which energy is transferred in astrophysical systems. The jets of particles that are often observed erupting from the poles of rotating black holes are another testament to the extreme physics at play. These relativistic jets, moving at speeds close to that of light, are thought to be powered by the black hole's rotation and magnetic fields, and they can extend for hundreds of thousands of light years, influencing the evolution of entire galaxies. Understanding how these jets are formed and collimated requires a deep understanding of magnetohydrodynamics in regimes far beyond anything we can simulate or experiment with on Earth. In essence, black holes act as cosmic crucibles, forging conditions that allow us to witness and study the fundamental forces of nature operating at their most intense. They are not merely cosmic curiosities. They are invaluable natural laboratories that enable physicists to test the limits of our current theories and to search for new physics that can explain the universe in its most extreme manifestations. The data we gather, whether through direct observation of gravitational waves, the analysis of electromagnetic radiation from accretion disks, or the theoretical exploration of quantum gravity near singularities, all contribute to a more profound and complete understanding of the cosmos and our place within it. Within these cosmic crucibles, the universe reveals its most profound secrets, teaching us about the very fabric of existence. The future of the universe might be shaped by black holes. The grand narrative of the cosmos, stretching across unimaginable eons, is not a static tapestry but a dynamic, evolving entity. And at the heart of this unfolding story, playing a role far more profound than mere cosmic curiosities, are black holes. These enigmatic objects, born from the violent demise of colossal stars or coalescing from primordial matter, are not just passive participants in the universe's grand design. They are active architects, subtly and profoundly influencing its ultimate destiny. Consider their immense gravitational power. As they continue to accrete matter, growing larger and more influential, their gravitational pull shapes the very structure of galaxies. They are the anchors around which stellar systems orbit, the gravitational wells that dictate the trajectories of gas clouds and nebulae. This gravitational influence is not confined to the local neighborhood of a galaxy. The collective gravitational effects of supermassive black holes at galactic centers can influence the large-scale distribution of matter in the universe, contributing to the formation of the cosmic web. The vast, filamentary structure of galaxies and dark matter that crisscrosses the cosmos. Beyond their direct gravitational influence, black holes are also powerful engines. The energetic processes occurring in their accretion disks and the colossal jets of plasma that can erupt from their poles inject vast amounts of energy into their host galaxies and the intergalactic medium. This energy can trigger or suppress star formation, alter the chemical composition of gas clouds, and even influence the behavior of entire clusters of galaxies. Over cosmic timescales, these energetic feedback mechanisms can play a crucial role in regulating galaxy growth and evolution, essentially dictating the rate at which new stars are born and how galaxies interact with each other. Furthermore, the very existence and eventual fate of black holes are intertwined with the long-term evolution of the universe. While they are incredibly durable, black holes are not eternal. Through the process of Hawking radiation, they are predicted to slowly lose mass over unfathomably long timescales, eventually evaporating entirely. This process, though infinitesimally slow for stellar and supermassive black holes, represents a fundamental aspect of the universe's eventual thermodynamic equilibrium. The ultimate disappearance of black holes signifies a final stage of cosmic evolution, where all organized structures have dissipated, and the universe approaches a state of ultimate uniformity and stillness. The mergers of black holes, events that generate powerful gravitational waves, also contribute to the universe's ongoing transformation. These colossal collisions are not just dramatic spectacles. They are moments of profound cosmic change, reshaping the gravitational landscape and redistributing mass and energy. As the universe continues to expand and stars eventually exhaust their fuel, the remaining black holes will persist, their gravitational influence continuing to shape the distribution of matter and energy. They will remain as the dominant gravitational entities, dictating the slow, majestic dance of the cosmos in its twilight years. The very fabric of spacetime, warped and stretched by their presence, will continue to be molded by their enduring power, guiding the universe towards its ultimate, quiet conclusion. In their enduring presence, black holes remind us that even in the deepest, darkest cosmic voids, there is a profound and shaping influence, a silent hand guiding the universe towards its eventual, peaceful repose. Black holes offer a glimpse into the ultimate fate of matter. Imagine, if you will, the very end of a cosmic journey for a piece of matter. Not a gentle fading, but a profound transformation, a descent into the ultimate unknown. Black holes are, in essence, the final resting places, or perhaps more accurately, the final asterisk transformation zones for matter that has exhausted all other possibilities. When a star, many times more massive than our own sun, reaches the end of its life, it no longer possesses the internal nuclear furnace to resist the relentless pull of its own gravity. This gravitational collapse is catastrophic, leading to a supernova explosion that blasts much of the star's outer layers into the cosmos. But for the core, the story is different. If the core is massive enough, gravity overwhelms all other forces, compressing the matter into an infinitesimally small point, the singularity. What happens to the matter that crosses the event horizon of a black hole is a subject of intense scientific debate, but the prevailing understanding is that it is irrevocably altered, its constituent particles crushed and stretched beyond recognition, its very identity as a distinct entity seemingly erased. This is not a destruction in the sense of simple annihilation, but a transformation into something fundamentally different, something that contributes to the immense mass and gravitational power of the black hole itself. It's a process that redefines what it means for matter to exist. The familiar laws of physics, as we understand them in our everyday experience, break down at the singularity. Concepts like space and time become warped and distorted to an unimaginable degree. Matter that enters a black hole is not merely stored. It is subjected to forces that would tear apart any known structure, any atom, any particle. It is a realm where the very definition of stuff is rewritten. Consider the ultimate fate of a star, a planet, or even a stray atom that ventures too close. It is pulled inexorably towards the center, its journey marked by increasing gravitational forces that stretch it, a process poetically termed spaghettification. This stretching is not just a physical distortion, it's a fundamental alteration of its state. The matter, once perhaps part of a vibrant nebula or a solid planet, is compressed and integrated into the black hole's immense gravitational well. It becomes part of the black hole's mass, its charge, and its spin, the only three properties a black hole is believed to possess according to the no-hair theorem. So, while we cannot observe the matter inside a black hole, its ultimate fate is to become an integral, albeit transformed, component of this cosmic enigma. It is a stark reminder of the universe's capacity for profound change and the ultimate dominion of gravity. The matter may be lost to our current observational capabilities, but it is not truly gone. It has merely entered a new, extreme phase of existence. This process underscores that even what appears to be an end is, in the grand cosmic scheme, a transformation, a redistribution of fundamental cosmic ingredients. The ultimate fate of matter in this context is to contribute to the very fabric of these enigmatic objects that shape the universe. The black hole itself is, in a way, a repository of these transformed destinies, a testament to the universe's relentless capacity for change. It is a profound thought that the very substance of the cosmos, when pushed to its absolute limits, coalesces into these powerful, mysterious entities. The ultimate fate of matter within a black hole is to become part of the universe's most extreme gravitational structures, a silent, yet powerful testament to cosmic evolution. It is a glimpse into a realm where matter is not destroyed, but fundamentally reconfigured, contributing to the immense gravitational tapestry of the cosmos. In the silent embrace of a black hole, matter finds its ultimate transformation, becoming a whisper in the grand cosmic symphony of existence. The quiet hum of the universe is punctuated by black hole events. Imagine the universe as a vast, silent ocean, where the gentle, pervasive hum of cosmic background radiation is the constant, underlying melody. For eons, this quiet symphony has played, a testament to the Big Bang and the slow, steady evolution of stars and galaxies. But within this seemingly tranquil expanse, there are moments of profound, dramatic punctuation, events so powerful they momentarily drown out the background hum, leaving an indelible mark on the cosmic soundscape. These are the events orchestrated by black holes. They are not merely passive voids. They are dynamic actors in the grand cosmic drama, their existence and actions shaping the very fabric of space-time and influencing the evolution of everything around them. Consider the birth of a stellar mass black hole. When a massive star exhausts its nuclear fuel, it collapses under its own immense gravity. This catastrophic implosion culminates in a supernova explosion, a blinding flash of light that can outshine an entire galaxy for a brief period. The outer layers of the star are flung into space, enriching the interstellar medium with heavier elements, the very building blocks of planets and, ultimately, life. But at the heart of this cosmic fireworks display, the core continues its implosion, crushing itself into an infinitely dense point, a singularity, and forming a black hole. This violent birth is a dramatic punctuation mark, a sudden, explosive crescendo in the universe's quiet hum. The gravitational waves generated by this collapse ripple outwards, a tremor in the space-time fabric that can be detected by sensitive instruments here on Earth, a faint echo of the cosmic violence. Then there are the mergers of black holes. When two black holes, orbiting each other, eventually spiral inwards and collide, they release an astonishing amount of energy in the form of gravitational waves. These waves are not light or sound. They are distortions in spacetime itself, propagating at the speed of light. The LIGO and Virgo observatories have detected these ripples, providing direct evidence of these cataclysmic mergers. Each detection is like hearing a sudden, powerful chord struck in the universe's symphony, a brief but intense burst of energy that momentarily overwhelms the ambient hum. These events are not only spectacular, but also crucial for understanding the population and evolution of black holes, revealing how they grow and interact over cosmic timescales. The activity around supermassive black holes also contributes to these punctuations. As matter, such as gas and stars, falls towards a supermassive black hole at the center of a galaxy, it forms an accretion disk. This disk spins at incredible speeds, heating up to millions of degrees due to friction and gravitational forces. The intense radiation emitted from these accretion disks, particularly in the form of X-rays and gamma rays, can light up the cores of galaxies, creating quasars and active galactic nuclei. These are some of the most luminous objects in the universe, their brilliance a stark contrast to the otherwise dim background. The powerful jets of plasma that are often ejected from the poles of these supermassive black holes, traveling at near light speed, are another form of cosmic punctuation, carving out vast cavities in the surrounding intergalactic medium. These energetic outflows can influence the star formation rates of entire galaxies, demonstrating the profound impact these seemingly inert objects have on their cosmic surroundings. Even the subtle, long-term processes associated with black holes, like Hawking radiation, represent a form of cosmic punctuation, albeit on an almost imperceptible scale for us. While incredibly slow, the gradual evaporation of black holes through the emission of particles is a continuous, albeit faint, contribution to the universe's energy budget. It's like a very, very low-frequency note that has been playing since the dawn of time, a constant, subtle alteration to the cosmic hum. These dramatic events, the birth of black holes, their mergers, and the energetic outflows from their active phases, are not just isolated incidents. They are integral to the dynamic evolution of the universe. They stir the cosmic pot, redistribute matter and energy, and influence the large-scale structure of the cosmos. Without these punctuated events, the universe would be a far more static and less interesting place. They are the moments that remind us of the raw power and immense scale of the cosmos, the moments that break the monotony and reveal the underlying forces at play. The quiet hum of the universe is not a sign of stillness, but of a deep, underlying rhythm, a rhythm that is profoundly punctuated by the dramatic, awe-inspiring actions of black holes. Understanding black holes brings perspective to our place in the cosmos. When we contemplate the immense gravitational forces at play within a black hole, the sheer scale of its existence, and the profound alterations it enacts upon the very fabric of space-time, it invites a deep and humbling contemplation of our own place within the grand tapestry of the universe. Imagine, if you will, a region of space so dense, so powerful that nothing, not even light, can escape its embrace. This is not a mere theoretical construct. These are tangible, albeit invisible, entities that shape the cosmic landscape. The existence of black holes, with their insatiable appetite for matter and energy, their ability to warp the paths of distant stars and galaxies, and their role as architects of cosmic structures, forces us to confront the vastness and the dynamic nature of the universe in a way that few other phenomena can. Consider the sheer contrast between the fleeting nature of our individual lives and the seemingly eternal, or at least incredibly long-lived, existence of a black hole. While we measure our years, our decades, our centuries, black holes operate on timescales that dwarf human comprehension. The birth of a stellar mass black hole, the remnant of a colossal star that collapses under its own gravity, is an event of cosmic significance, a violent supernova that seeds the interstellar medium with heavier elements, elements that will eventually coalesce to form new stars, new planets, and perhaps new life. Supermassive black holes, lurking at the hearts of galaxies, are even grander in their influence, orchestrating the growth and evolution of entire galactic structures over billions of years. Their gravitational pull dictates the orbits of stars, influences the formation of new stellar populations, and can even quench star formation through powerful outflows of energy. This immense scale and power, when viewed from our relatively small and ephemeral existence, can be both awe-inspiring and, at first glance, perhaps a little disorienting. It can make our everyday concerns seem insignificant, our personal dramas trivial in the face of such cosmic might. Yet, this is precisely where the perspective-shifting power of understanding black holes lies. It is not about diminishing our importance, but rather about contextualizing it. We are part of this grand, interconnected system. The very atoms that compose our bodies were forged in the hearts of stars, and the elements that make up our planet, our sun, and indeed the black holes themselves, all share a common cosmic origin. The study of black holes, with their seemingly paradoxical nature, regions of immense density yet devoid of visible light, points of infinite gravity yet governed by elegant physical laws, encourages us to embrace the unknown, to accept the limits of our current understanding, and to marvel at the sheer ingenuity of the universe. It reminds us that reality is far stranger and more wonderful than we can often imagine. When we look up at the night sky, knowing that these invisible giants are out there, shaping the very galaxies we see, it imbues the cosmos with a deeper, more profound sense of mystery and grandeur. Our own existence, therefore, becomes not an isolated event, but a fleeting, yet precious, expression of the universe's ongoing cosmic narrative. The vastness that once might have felt isolating now feels like a shared home, a grand stage upon which all phenomena, from the smallest particle to the largest black hole, play their part. This understanding fosters a sense of peace, a quiet acceptance of our place within this immense and dynamic cosmos, a place that is both humbling and deeply, profoundly beautiful. In the quiet contemplation of these cosmic titans, we find a gentle reminder of our fleeting presence within an eternal, ever-changing universe. The mysteries of black holes inspire awe and wonder. Black holes, in their profound and silent existence, present us with some of the universe's most enduring enigmas, and it is precisely these unanswered questions, these vast expanses of the unknown, that ignite within us a deep and resonant sense of awe and wonder. They are not merely celestial objects, they are cosmic question marks, challenging our very comprehension of reality. Consider, for instance, the nature of the singularity at their core. Our current laws of physics, so adept at describing the universe on scales from the subatomic to the galactic, falter and break down completely when confronted with the infinite density and curvature of space-time predicted at the heart of a black hole. This is not a limitation of our observation, but a fundamental boundary of our theoretical understanding. It is a place where the rules we know cease to apply, a testament to the fact that the universe holds secrets far grander than our current models can accommodate. This intellectual frontier, this place where our knowledge ends and speculation begins, is a fertile ground for awe. It reminds us of the sheer immensity of what we do not yet grasp, and in that vastness, there is a peculiar and comforting beauty. Furthermore, the very concept of an event horizon, that one-way membrane beyond which no information, no light, no traveler can ever return, is a source of profound wonder. It represents an absolute boundary, a cosmic threshold that dictates the fate of anything that crosses it. The implications of this are staggering, suggesting a universe where certain regions are fundamentally inaccessible, forever hidden from our view. This inherent secrecy, this profound inaccessibility, only amplifies our curiosity and our sense of the extraordinary. The universe, in its black hole manifestations, is not a simple, predictable machine, but a realm of profound mystery, where the familiar laws of cause and effect can be stretched to their absolute limits, or perhaps even beyond. The ongoing quest to understand these phenomena, to probe their depths with ever more sophisticated instruments and theoretical frameworks, is a journey fueled by this intrinsic human drive to explore the unknown. It is this very unknown, this vast, silent and powerful presence in the cosmos, that evokes in us not fear, but a deep, contemplative wonder. It is a reminder that the universe is far more complex, far more intricate, and far more surprising than we can possibly imagine. And in that realization, there is an unparalleled sense of majesty. In the silent depths of the cosmos, black holes whisper of a universe far grander than our minds can fully grasp, and in their profound mysteries, we find a quiet, reflective awe. We are all connected to the grand cosmic dance, even through black holes. Consider this profound truth. The very fabric of our existence, the atoms that compose us, the energy that sustains us, are all woven from the same cosmic threads that bind the most enigmatic objects in the universe, black holes. The elements heavier than hydrogen and helium, the building blocks of planets, stars, and ourselves, were forged in the fiery hearts of stars. When these massive stars reach the end of their lives, they can collapse under their own immense gravity, giving birth to stellar mass black holes. This act of cosmic creation and destruction, this fundamental process of stellar evolution, is directly linked to the very matter that makes up our bodies. The iron in our blood, the calcium in our bones, the carbon that forms the basis of all organic life. These were all once synthesized within stars, and their ultimate fate, in many cases, is tied to the processes that lead to the formation of black holes. Furthermore, the immense gravitational influence of supermassive black holes at the centers of galaxies, including our own Milky Way, plays a crucial role in shaping the very structures we inhabit. These colossal entities, though seemingly distant and abstract, influence the orbits of stars, the distribution of gas and dust, and the overall dynamics of galactic evolution. The spiral arms of our galaxy, the very neighborhood in which our solar system resides, are shaped by the gravitational ballet orchestrated by Sagittarius A. This means that the very environment that allowed for the formation of our sun and planets, and subsequently life on Earth, is intrinsically linked to the presence and activity of these cosmic behemoths. Even the faint whisper of gravitational waves, ripples in spacetime generated by the cataclysmic mergers of black holes, carries echoes of their immense power across the cosmos. These waves, traveling at the speed of light, are a testament to the interconnectedness of all celestial bodies. They are the universe's way of announcing its most dramatic events, and in their passage, they remind us that no corner of the cosmos is truly isolated. The energy released in these mergers, the distortion of space-time, affects everything everywhere. Think, too, about the fundamental forces at play. The same gravity that keeps us grounded on Earth is the force that governs the formation and behavior of black holes. The same quantum principles that govern the behavior of subatomic particles are being probed and tested in the extreme environments around these objects. We are not separate observers of the universe. We are participants. The very laws of physics that we discover and study are the same laws that govern the most extreme phenomena imaginable. The light that travels from distant galaxies, carrying information about their past, has been bent and distorted by the gravity of intervening black holes. This means that even the light we see, the visual information that shapes our understanding of the universe, has been touched by these cosmic entities. Our perception of the cosmos is, in a very real sense, filtered and sculpted by the presence of black holes. The concept of conservation of energy and momentum, fundamental principles that govern all physical processes, also applies to black holes. While matter that falls into a black hole seems to disappear, the total energy and momentum of the system are conserved, albeit in ways that are still being explored and understood. This interconnectedness, this adherence to universal laws, further emphasizes that black holes are not alien entities but integral components of the cosmic machinery. The very existence of black holes and the processes that lead to their formation and influence are part of the grand, ongoing narrative of the universe. The atoms that form our bodies were once part of stars, and those stars are part of galaxies, and galaxies are shaped by supermassive black holes. This intricate web of cause and effect, of cosmic creation and transformation, means that in a very real and fundamental way, we are connected to these celestial mysteries. The universe is a single, vast, and interconnected system, and black holes, in all their awe-inspiring power and mystery, are an undeniable part of that grand, cosmic dance. And so, as the stars continue their silent, ancient waltz, know that even the most profound cosmic phenomena are threads in the same tapestry that holds you, reminding you of your deep and inseparable connection to the universe. Our calm exploration has covered the profound principles of black holes, from the chilling certainty of the event horizon to the mind-bending concept of singularity. We have traced their violent birth from dying stars, their colossal influence at galactic centers, and their subtle, cosmic shaping of the universe through space-time warping and the emission of gravitational waves. We've touched upon the paradoxes they present, the slow evaporation predicted by Hawking radiation, and the sheer, majestic power they wield. Tonight, we have reviewed the principles of these enigmatic cosmic entities, reminding us of the vastness, the complexity, and the sheer, quiet wonder of the universe we inhabit. These phenomena, so alien and so powerful, are nonetheless a part of the grand tapestry of existence. In understanding them, even a little, we gain a profound sense of perspective on our own small, yet significant, place within this immense cosmic ocean. The universe is not a place of chaos, but of magnificent, ordered processes, even in the most extreme corners. And as we reflect on the immense forces at play in the cosmos, on the silent, inexorable pull of gravity and the bending of time and space, it is perfectly natural to feel a sense of profound calm wash over you. The worries of the day, the anxieties that may have kept you restless, begin to feel smaller, less significant when viewed against the backdrop of cosmic grandeur. You are a part of this universe, a speck of stardust imbued with consciousness, capable of contemplating such wonders. It is time to rest now. Allow the quiet understanding of these cosmic principles to settle deep within you, a gentle lullaby of scientific truth. Let the vastness of space and the profound mysteries of black holes soothe your mind, carrying away the tension and the stress. Sleep well, seeker of quiet wonder. Good night. If you happen to still be awake, you can drift into the next chapter now, continuing your journey through the serene landscapes of scientific discovery.